we will continue with the presentation of string functions in MonetDB. Next function will be field function. I will run this statement, and what this function do is that it is searching for this first string in a list that is made of all other arguments of this function. So A in this list of arguments will be at the first place, but the result is 0 because we are using zero-based indexing. In this second example, we are searching for letter B inside of the same list. So letter B would be at the second position, but if we are zero-based, then the result will be 1. If we cannot find our string in a list of other arguments, then the result of field function will be null. We also have a function that will calculate a hash of our string. We are calculating MD5 hash, and that hash will be 32 hexadecimal characters. Next function is split part function. This function will start with some string, and inside of that string we have some delimiters. For example, this is a delimiter in this case. We have to tell to Monet what delimiter to search for, and then this string will be breaked by this delimiter into several strings, and that will be a list of strings, and we will then take the third element of that list. In this case, this will be the third element because this is first element, second element, third element. So let's see the result of this function. So we will get the third element. And we also have some function that will return the size of a blob. So these are blobs. So this here is the same blob as this here. And we can apply function length to get the size of this blob in bytes, or we can also apply octet length, which is just a synonym for length. So these are the same functions. So when we run this, we will see that this blob has 3 bytes. I will now clear my screen. Next, we will talk about string metrics. String metrics are measurement used to calculate how much two strings are similar. For example, we have a string Tom and we have a string Tommy, and we want to calculate how much these two strings are similar or not. Before doing the comparison, we can apply some normalization on those strings, and for that we can use already familiar QGram normalize function. This function will remove all of the strange characters, so only numbers and letters will remain, and spaces, and all the letters will be transformed to uppercase. And we are doing this in order to standardize our strings so we can more easily compare them. Now, how do we do comparison? Well, for that, let's assume that we want to transform the word kitten to word sitting. So first, the word kitten will be changed by changing letter K to letter S. So we will get sitten. And then we will transform letter E to letter I, so we will get sitting. And then we will add G at the end, so we will get sitting. So we need 3 steps. This first step is replace, second step is replace, and then we have 1 step insert. We also can use delete of 1 letter as a step. So we need 3 steps. We can calculate these 3 steps by using Levenstein function. So I will copy this statement here. I will go to terminal. I will paste that statement. I will run it. And we can see that we need 3 steps to transform this word into this word. And Levenstein function will tell us how many steps do we need. Next, we will see that beside the Levenstein function, we also have Demerol Levenstein function. So what is the difference? Well, with Levenstein function, we are taking in account inserts, deletes, and updates. But Demerol Levenstein function also has transpositions. So what is transposition? Well, let's assume that we have 2 neighboring letters and we want them to switch their positions. So for example, instead of AC, we will have CA. So this is 1 transposition, and in Demerol Levenstein function, this is 1 step. But in Levenstein function, this would be 2 steps because we have to update 2 letters. So that is the difference. Now, in MonetDB, it doesn't matter whether we are using the name Levenstein or Demerol Levenstein, they are the same function. So let's copy this example from here, and we will see that both this function will return number 2. So I will run this, so we get the result 2. So what does it mean? It means that we need 2 updates, and that means that it doesn't matter whether we use this name of a function or this name of a function, we will get the result that is characteristic for Levenstein function. But how to get the behavior for Demerol Levenstein function? Well, easy. I will go back. In that case, we just have to use 5 arguments. So I will copy this, I will paste it here, I will run it, and now the result is 1. Now this is counted as 1 transposition. So in this case, this function and this function are working as a Demerol Levenstein functions. Now, what are these 3 arguments? Well, these are the costs for insert and delete, for update, and for transposition. So if we are using 5 arguments, then our functions are working as Demerol Levenstein function. But if we are using 2 arguments, then our functions are working as Levenstein function. I will now clean my screen. Let's assume now that the cost of transposition is 3 points. So we can use a function like this one. So this last argument is 3. And if I run this, we can expect only 1 transposition from AC to CA, so the cost should be 3. But we will get the cost 2. And this is because there are several ways how to transform this word to another word. Let's go to this web page again, and we can see that instead of using transposition that will cost us 3 steps, we can first delete this letter A, and then we can insert it on the right side. So we have 1 deletion and 1 insertion, and because their cost is 1, then total cost will be 2 points. Or we can update our letters. We can update A to C, and we can update C to A. So we have 2 updates. Cost of each update is 1. So again, total cost will be 2 points. So Levenstein function will always return the minimal cost needed to transform one word to another. Let us now see one more version of Levenstein function, and this is the version with 4 arguments. In this case, this is the cost of deletes, this is the cost of updates. In inserts always cost 1 point, and there are no transpositions. So transpositions are not possible here. We only have inserts that cost 1 point, we have deletes that cost this much points, and we have updates that cost this much points. So in this first case, we know that we can transform this string to this string by 1 deletion and 1 insertion. So we can first delete the letter A, and then we can add it on the right side. And because the cost of deletion is 2 and the cost of insertion is 1, total cost will be 3. So that is how this version with 4 arguments work. Beside this, we also have 2 similar functions. They are basically Demerol Levenstein functions with a different name. So we can only supply 2 arguments, but when we are using added distance, the costs will be always 1, except for transposition when the cost will be 2. So in this case, the result will be 2 because we need either 2 updates or 1 transposition, but transposition cost is 2. On the other side, we also have a function with name added distance 2. So now we have this number 2 at the end of a name of a function. In this case, cost of inserts, deletes, updates, and transpositions is 1. In this case, we only need 1 transposition, so the total cost will be 1. I will now clear my screen. Next function, we will take a look at Jarrow-Winkler function. So this is it. I will run this statement, and if 2 strings, so this string and this string, are the same, in that case, Jarrow-Winkler will return 1. If they are similar, for example, they are ACA and CAA, the result will be somewhere between 0 and 1. But in this case, Jarrow-Winkler considered that these 2 strings are not similar, so the result will be 0. Now, when comparing 2 strings, Jarrow-Winkler will put bigger weight to similarity if those 2 strings have the same prefix. and the bigger that prefix is, so the more we have letters at the start of a strings that are the same for one string and for another string, the bigger the boost will be. So German people prefer words with the same prefix. I will now clean my screen. At the end, we will talk about soundX function. SoundX function is useful only for English language. I will run this statement, and here we can see the result of SoundX function for the word rose. The result will have 4 characters. First character will be R, because this word is starting with R, and then we will have 3 digits. These 3 digits will depict how this word should be pronounced. And according to SoundX function, this word rose and rose should be pronounced in the same way, because the code will be the same for these 2 words. We have R200 and R200. For these 2 words here, SoundX think that they are different, so we will get different code. Here we have W200 and here we have W320. And for words table and fork, SoundX think that they are even more different, so we will get 2 significantly different codes. Now, how to compare words by using SoundX? Well, we can achieve that by using difference function, and here is a difference function. I will run it. So what this difference function do, it is that it will use the codes returned by SoundX function, and then it will compare those codes. Here we have no differences, so the result is 0. But here we have 2 digits here that are different for this first string than for this second string, so the difference is 2. And in this last example, table have this code, but first 3 characters are different than first 3 characters for the fork, so the difference is 3. And this is how we can use difference function to compare words, but only if they are from the English language.